So, welcome. Series 2. This is episode 7, and all the subjects that we share each month, certainly this season and probably season 3, they're all suggestions by you lot, the sort of things that you'd like to hear, and then I have to go away and scratch my head. And when someone asked for connectors and cabling, I really wasn't entirely sure what on earth I could say that would be of some value, but as it turned out, I ended up taking a whole load of material out. So I really can't cover the entire subject of cabling for us. As I mentioned earlier, you're really welcome to put your microphones on. I positively encourage interruptions and questions, and if anything's not clear or if you want me to go over anything again, I'm all happy to do that. Hopefully I know the answers to your questions. Usually I talk about 5 parts of a particular topic, so it can look like a little bit of a marathon run, and then there's opportunities at the end, you know, share comments, ideas, thoughts, your own experiences. So that's the general theme. You can put your microphone on, Ruth, if you like. Looking very laid back there, Ruth. So the presentation which I've put together for us, it is available to download. Hopefully, just make sure my screen is on here properly. Hopefully you can see the screen I'm presenting. Yep, so hopefully that's there. Everything I've got here, everything's available to download. So if the screen goes wonky, or you want to make any notes on anything, it's all available to download. It's already up there for you. I put it all together here. So I'm looking for something which I might have to grab in a second. Right, hang on, let me just grab something which I think I'm going to want. 1 second, everybody. Right, yes. Just pop this in here. We've got a semi-practical, and I'm going to want a Excel spreadsheet for that, which I put together for us. Right, I'll open that in just a moment. Right, okay, so cables and connectors and cabling. Oh, hang on, I've got too many things on my screen here. Can't see everything. Right, we'll come to that in a second. Right, so I did a little bit of an internet search, and I found this. So how that works, I have absolutely no idea. I'm sure it didn't start like that. And the other picture I found, which I'm sure we've all seen this in the high street.
Stephen?
Yep.
You're still showing your startup banner. I don't know if you mean to be doing that, but
hang on a second. Your screen is paused. Right. Thank you for hang on a sec. Let's try that again. Let's try that again. Right, let's try share. That's better, isn't it?
Yes.
Right, thank you. Just occasionally, my internet also occasionally does shenanigans and drops out, and then I'm left talking to myself. So if that happens, just pop the kettle on, and I'll try and come back to it. Right, thanks, Ruth. Right, okay. As I was just sort of talking to myself, probably. Bit of an internet search. This is a typical wiring nightmare in my view. How these things work, I have absolutely no idea. How do you debug that sorry mess? And the other one, I'm sure I've seen this in New Delhi, probably where this picture was taken, another absolute rat's nest of cables. And what I will say is, ever you want to introduce a problem into your electronics, add a cable. Cables are the undoing of everything. So how we choose them and how we bang signals down it is what I thought we could have a little look at. So that's just a little montage there of 2 sorry looking cables. In case the picture froze and you didn't see it, these slides, they're all downloadable. They're all free. If you just skip onto my website and scroll down to downloads, you'll see how to design electronics folder, and you'll see season 1, season 2. And if you go to season 2, number 7 is where we are right now. So things I was going to look at for us today were types of cables, voltage drops on cables, shielding, bit on EMC, that's always important with cables, and then a tiny bit on connectors. And yeah, if you have any questions or anything, please just shout. You're very welcome. What I will say, if you leave your microphones on, you shout. If you do take a phone call, please remember to mute it. Otherwise, we will get to listen in. Right, so let's start with cables and types of cables. So common ones, which you and I will be playing with more often than not, I should think. Twisted pair is the first one. So what on earth is that? They're used very much for Ethernet. In fact, any signal where you may have a signal going positive and the other line going negative, which is called a differential, often you'll put those over what's called a twisted pair. And it is exactly what it says in the tin. For those who haven't seen this, it's just a pair of wires which are twisted together. You can see that these ones here, this photograph I grabbed, everything's sensibly colored. And the idea of the twisted pair is an induced electric or magnetic field will cancel itself out. And that's just by the very physical nature that these wires are wound. So because they're wound, and I can draw one here, hopefully, maybe I'll choose a different color to blue. So you may have a field going that way, and of course a field going the other way, which ordinarily, whether electric or magnetic, ordinarily that would induce noise onto your signal, onto your cable, which could be a bad thing. So provided you've got a nice differential circuit, and we'll have a little look at some ideas a little later, you can then cancel out noise. And these will be used things like RS485, for example, which is a differential signal, one signal positive, one negative, or 422, which is full duplex for differential signals. Ethernet, that's a differential signal. That would use twisted pair. USB, there's another one. If you look at, you have positive and minus data, there's another differential signal. If you're taking I2C off board or SPI, you can make that differential. So in my view, if I'm taking signals off a board and I'm going to transmit over any distance, probably anything longer than about a foot easily, I will probably always want to go differential. And we'll have another look as to why that helps when we talk about EMC, one of my favorite subjects. The other cable is that we'll probably play with quite a lot, is just good old-fashioned ribbon cable. This looks a little bit 1980s with its fancy colors, but it's certainly, in my view, it makes life easy. So if I have the chance to use multicolored ribbon cable, I'll probably definitely go with that. And what we'll have a look when we look at shielding, I'll show you sort of how you can make the best effort to eliminate any noise induction into your cabling. Other cabling, I haven't got one here actually, I was going to grab one. Your mains flex. So, yeah, brilliant, there's not one here. So mains cable, obviously it's a little bit chunky. And in fact, I'll draw on the other side of this. With mains cabling, something else I'll tell you about that ribbon cable. So with mains cabling, that's the core in the middle there. you have quite a thick insulation for mains cabling because it's high voltage. One thing I found absolutely amazing, I looked up the data sheet because I've seen this before for ribbon cables. And if you look up the voltage rating for a ribbon cable, it'll probably tell you it's good for 300 volts. Absolutely do not put that sort of voltage down a ribbon cable. One thing, years ago, a friend of mine bought a house, and the DIY enthusiast before him wanted to run a power cable across the room, but of course that put a ruck in the carpet. So they used ribbon cable because they said it's good for 300 volts. Patently, it's not up for it. The reason it's not up for it, it's not so much the core isn't good for it, it's more the insulation just plain isn't safe. If you're using electrical mains on any cables, normally you'll see something called tri-rated. And what that means, it's flame retardant, usually good for 105 volts. And it has a thick insulation, which I believe will be something like 0.4 or 1.2 millimeters. So quite thick insulation for anything mains orientated. I'm sure if we've all stripped leads for mains plugs, you know what the cable looks like. So there's a tiny bit on cables, types of cables.
Stephen,
yeah,
did you just write that word down? You said the rated thing.
Right, yes, indeed, it is. Here we go. It's called tri-rated.
Oh, right, okay.
There
Thanks.
you go. I'm not sure all the three are. I should have looked that up, really. But it's what it means. It's a flame retardant. I've written it here, so I'm just reading it. It's suitable for high working temperatures, up to 105 volts. Typically, it's used for electrical installations, and it's got what's called double insulation, which means the thickness of the cable is quite thick, so it's then safe, and that's quite an important thing. Yeah, brilliant. Anyone got any questions as we tickle along? Please stop or chime in if you disagree. Right. Okay. So next thing I wanted to share with you are voltage drops in cables. Now then, I'm going to swap to a spreadsheet in a second because I've done a little bit of maths and we can see how voltage drops in cable lengths and cable thicknesses can affect you. So about a year or two ago, I worked on a project where it was a factory machine. They ran a cable from a cabinet, which meant in this picture here, maybe it's something like here, for example, there's the cabinet. They ran a cable all the way along and, around a few corners. In fact, it was 18 meters worth of cable, and they didn't get the voltage that they wanted at the other end. In fact, also because there was a voltage drop in the cable because it was so long, it caused the system not to work properly. And it took a little while to figure out what had gone wrong and, of course, how to fix it. So what I thought we could have a little look at is what is the calculations behind working out a voltage drop in the cable and how do we compensate for it. So any cable is essentially just a resistor. So what I've done here, this is our cable. Obviously, it's got a cross-sectional area, which I've done in sort of a yellowy color. Can I just turn that up at all? Just trying to turn up the, that's as high as it goes, the exposure on the camera. The cross-sectional area and the length and how much current we want to put down it will very much dictate the voltage drop across the cable. And don't forget, if you've got a long cable, it's going to be the distance from, say, your power supply to whatever you're trying to power and coming back. So the project I was working on, the unit was about 20 meters from the power supply. But don't forget, it had to go there and back. So actually it was 40 meters. And yeah, there were problems. So I thought we could have a little look at how do you calculate that. So it's a dead easy equation. So we're looking at the resistance of the cable, since that's essentially what it is. Resistance is voltage divided by current, or as my grandfather said many years ago, very important rubbish. And resistance is also defined by the length times the material's resistivity divided by the cross-sectional area. That's all we need to work out what the voltage drop is. And for a copper cable, which is why I put Cu, the chemical symbol for copper, this is someone's worked out what the resistivity is for a cable. And so all we need to do is plumb that number into our equation. We can easily rearrange it. So if we want to know what the voltage drop is here, we can just multiply this side by a current and multiply this side by a current, and that'll give us a rearranged equation. Hopefully that will make sense. And then we just need to start plumbing some numbers in, and we can get an idea of what the voltage drop might be. So I am going to open up Excel for us, and hopefully I'll swap to it if it opens correctly. We can then have a look at what happens. Right, okay, so I'm going to attempt to unshare and change to a different screen. So if you just bear with me. Right, okay, things are going wrong already. 1 second, everybody. Right, I'm just going to stop sharing that screen for us and try and reshare an Excel spreadsheet. So this spreadsheet is also available to download. And all I've done in this spreadsheet, just open it up, here we go. All I've done in this spreadsheet is dropped into it the equation, which we'll come back to in a second. And just so we can type in some numbers and it'll tell us what's going on. So, for example, hopefully you can all see this spreadsheet on here.
Could you possibly make the Excel window as small as? All right,
Is that working?
It's just if you make the window itself narrower.
Oh,
that
hang
helps.
on. Am I sharing the window rather than? Oh, hang on a sec.
You are sharing the window.
Right.
Just make the window narrower.
Is that working for you?
Much better.
Thank you. Thank you.
Although you could perhaps do the unzoom now as well.
Brilliant, brilliant. Is that? I hope that's working for everybody.
That's lovely.
Okay, thank you.
Sorry to be picky.
No, because trust me, when I'm here, everything looks brilliant on my screen. And, you know, knowing what it looks like at your end, and of course, with my internet drops out, it's all extremely helpful for me to see what's going on. Right, so look, so all I've done here, I've just put into the equation, here's my voltage drop, which if I enter all these magic numbers, and I can then calculate what my voltage drop is. So, for example, let's say I've got a cross-sectional area of a cable. Here I've got it as 2.9 millimeters, which is the American wire gauge 9, I believe. We'll come to that in a moment. It'll calculate for us based on the diameter what the cross-sectional area is. This is the resistivity of copper, which is given to us. And then we've got our cable length, which we've got as 20 meters. And then how much current we're going to shove down it. And then that'll very easily just tell us what the voltage drop is. So if we had a circuit which was running on 3.3 volts, and we were 20 meters away, then actually we'd need our power supply to actually be at 3.57 volts in order to accommodate the voltage drop in the cable. And so look, we can just see here, if we make this 40 meters, make that 40, fingers crossed, things start to get a little bit more ugly. If we up the current, of course, what have I done there? Oh, right, oh, that's something else I think I remember that. It's just experimenting with it. Yeah, if I up the cable to say 30 amps, then yeah, so the longer the cable and the more voltage and the more current we want to put down it, clearly you can see intuitively that the voltage drop is going to get larger and larger, and so we start to have to accommodate for it in the power supply. So possibly if you had a 3v3 power supply, here's a word to the wise, you'll probably find if you had a fixed DC power supply, usually have a bit of calibration on them. The chances of being able to calibrate a 3v3 power supply up to 6 volts is remote to none. So you'd have to go for a bigger power supply. Or you'd actually have to upgrade your cable. So this is the other way around it. So in this example, let's just have a cheap look at my next page. So if I was to increase the cable diameter to say, I'm going to call this, this is 16.8. Oh, that's meter squared, millimeter squared. Hang on a sec. Let's do it on this one here. Oh no, hang on. So, oops. So if we was to double that to say 6 millimeter diameter cable, suddenly the voltage drop is going to start to drop across the long cable. Intuitively, that makes a world of sense. But there's the proof. If you've got a long cable, how do you deal with it? And I think one of the key things to remember here when you're looking at cables is the cable diameter is always given in millimeters. So don't forget, if you do this calculation, to convert it to meters, just divide by 1,000 before you do the rest of the calculation, because the density, the relative materials resistivity is given in meters, and you're given your distance in meters, so you don't really want to have suddenly one unit in millimeters, because everything will go terribly, terribly wrong. Right, okay, and it's just a very simple piece of algebra. I didn't think it could go the other way. So if you had a 220, or with 240 for us, isn't it? If we had 240 volts, oopsie days, at 30 amps, and we had a 3 meter cable, 3 kilometers, that cable, isn't it? So, or 30 kilometers rather. So 30 kilometers of cable. You can see here just how big a cable this would need. So that would need a 9.1 millimeter diameter cable. So that's available to download, which is great. I am going to hop back to the other bit for us. One sec. Stop sharing and then share this bad boy again for us. Right, hopefully that's all back and lovely. So there's the proof that if you've got a lot of current and a long cable, you're going to get a very appreciable voltage drop. So it's just one to watch. And then the other thing which I just wanted to share here for us before we move on and look at shielding is AWG, which is the American wire gauge. So this is a standard table. You'll find this on the internet if you just type AWG cable sizes. They'll give you the cable size, wherever they came up with this number. They usually give you the cross-sectional area, always in millimeters, sometimes in inches. So watch that one. And they may give you the radius or diameter, which of course is just derived from area, which, just to remind anybody who's unsure, that would be pi d squared over 4. For anyone who just needs a little reminder as to how you get from diameter of a cable to area. Right, hopefully you're all still with me. Right, okay. Well, Wintor. Right, shielding. This is where things start getting a little bit complicated. Right, so if you wanted to put some shielding on a signal, because we'll talk in a moment about EMC, which is what this leads not quite nicely into. So there's a split in the thought process of, do you shield a cable at one end, or do you shield it, ground it, I should say. Do you ground it at just one end, or do you ground it at both ends? So I don't know if anyone's got an opinion which one they would want to go for. Deathly silence.
I'm going to go for one end.
You're going to go for one end, okay? So one for one end.
Because ground loops.
Yep. Okay. Yeah, you'll get ground loops. We'll come on to that in just a second. Anyone want to go for two ends?
Yeah, I'll vote for two ends.
Yeah, one for two ends. Anyone else? Right. Okay. The answer is not as straightforward as what you think, unfortunately. Going for one end, it'll be very good at screening electric field interference, but it won't be any good at screening against magnetic fields. If you screen it at both ends, if it's grounded at both ends, then you do stand the potential on a long cable of getting a ground loop, which could cause you a problem. We'll explain that in just a second, what will happen. But if you I had to look this up. If you ground it at both ends, then it'll be much better at screening against magnetic fields as well. So I think the moral of the story is it's horses for courses, and you just need to do what works for your application. That's my assessment. The danger of both ends is potentially you've now got a complete circuit, haven't you? So you've now got a complete circuit with both ends. So there is a danger if one is at one potential, let's say this is at 0.1 volt and this is at 0.11 volt, you're going to get a flow of current in the screen. And that flow of current in the screen could then couple straight onto your wire and maybe cause more problems than what it solves. And you're doing that maybe because your application has got, electromagnets running nearby. So if you just go with one end.
Just to explain, one of the situations in which ground loops are horrible is anything to do with audio. I presume it's because the potentially small audio signal, the audio signal is small compared to the potential pickup signal. So they're on a par in terms of levels, whereas with more traditional logic level signals, the logic level is higher compared to the potential pickup signal.
Yeah. So I've got here, this is my Bible. If anyone's doing any EMC work, this is the renowned Bible on EMC. It's a pity they haven't got a 5th edition for this. This is published, the principles of electronics haven't changed for a long time. This is copyright 2010, this edition. And so the section here, so how well you can see that here, but it's got here the two scenarios. So grounding at one end, I'll read this to you. It says good capacitance shielding, no magnetic shielding. Ground at both ends, and they say you'll get good magnetic shielding. But let me just read to you what they also say here, because it's difficult probably to see that. They say here, there are two problems with grounding the screen at both ends in the circuit that we have just up here. One is that it becomes a circuit conductor, and any voltage dropped across the screen impedance will be injected in series with the signal. So just as Ruth says, you're going to end up probably, certainly in audio, you're going to end up coupling any noise in the shield straight into your audio, which may be worse than terrible. Where they go on. Whenever a circuit is grounded at both ends, only a limited amount of magnetic shielding is possible because of the large interference currents induced in the screen ground loop. So there we go. So I think a lot of people just say go with one end, but as I've discovered, it kind of depends on your application. You know, it's whatever works, I suppose, is the moral of the story. And you find these things when you get to EMC testing. Right, okay, so there's a hot debate.
Can I just ask one question?
Yeah.
Does the resistivity / conductivity of the shield have any bearing on what we've just been talking about?
Oh my goodness, that's a very good question. And I suppose the answer has to be yes, doesn't it? Because we go back, good call. It's almost like we planned this. So if we go back here to our rather noddy drawing, yeah, the voltage, because it's essentially a resistor, isn't it? So I'll just write here, resistance, just to remind us all, is voltage over current. Yeah, or voltage equals current times resistance. You just have to rearrange that, don't you? So yeah, absolutely is the answer to the question. It would appear that is the case. So I suppose you're either going to want to up the rate of your cable. So the better quality of the cable, clearly the better it's going to be. Interestingly, one thing I will say for look at ribbon cables, what we can do about screening those. I worked on a medical product some years ago, and the waveform was really important to the product working. But of course, because of EMC, the cable had to be screened. But the problem with the screening, if that end was connected to 0 volts, was of course the screen was acted as a capacitance. So the long cable that they had, because it was essentially like a diathermy, which was like a pen with a long wire coming off the end. The cable itself was a resistor in sorry, not resistor, a capacitor, and that actually affected the waveform. So they wanted to get rid of the shielding in order to make the waveform correct, but as soon as they got rid of the shielding, then of course the EMC went off the charts. So it's always a balancing act, if that makes any sense for us all.
So what was the conclusion in the end?
The conclusion in the end was on that project, where it had to have shielding, and I got rid of as much shielding as I could, and I took it absolutely to the limit on what we could get away with. Because usually when you go to EMC testing, you put it on a table, like a dining table, pretty much made of wood, and you run out the room. Of course, you make everything right to the limit on the shortest possible cable you're allowed to have for the test. So in reality, the product didn't really reflect what was going on in reality, but we had to pull those tricks off in order to make it pass EMC without being overly detrimental to the waveform. So you know what, it's you never get what you want in electronics. It's all one massive compromise.
I was wondering whether you could reduce the capacitive effect of the cable by increasing the gap between the shield and the core.
Yeah, absolutely. The trouble is when you're doing any EMC work is, you're against the clock to get the thing out the door, and you're looking for what compromise that you can get away with. But yeah, if we'd gone for a wider cable, just brought here on here, where a larger cross-sectional area of insulation, then there's insulation there this time. With a wider insulation, probably not the best drawing in the world. Yeah, it would have dropped the capacitance. Yeah, that would have worked, maybe. Trouble is with screens, screens do not stop. It's like a metal box. Screens do not stop radios getting out. We'll talk about radio emissions in a moment. Screens do not stop radios getting out of cables and boxes. What screens do is they attenuate it. They don't stop it completely. Maybe in a moment, I'll just go grab a book. I've got it all written in, or maybe I'll hope for next time. Anyway, right, let me share something, move on here a little bit for us, otherwise we'll get waylaid in one subject. Right, I'm looking for, here it is. Right, so let's move on from that and let's look at how the earth do you screen a ribbon cable. So I've got a couple of examples. This is my example of a ribbon cable, and what I thought I'd do a couple with you and show you how you do it on a ribbon cable. So, if you take any old computer apart, you'll see that the things are absolutely stuffed with ribbon cables. So how do we do screening on something like this? That looks like a nigh impossible task. There's a number of things that you can do. And this is how, when I design boards, is how I do it. So I'll have that one as ground, 0 volts. Then I'll have a signal, I'll call it S1. The next one is ground. Then the next one is a signal, then a ground, then a signal. And I think you begin to get the idea. Yep. And this last one will be ground as well, of course. It is as easy as peasy as that. So if you look at a lot of IDC connectors, which have got 2 rows, you'll see one of those rows is usually all ground. If you've got yourself a BBC micro from the 1980s, if you look at the user port, or if you just open up the schematic online, for the BBC micro or any other computer, you'll see that one row is always ground and the other row is always signal, and that's so in the ribbon cable you get this topology. So oh, whoever's okay there, I hope.
Oh, sorry.
It's okay. The next question, of course, is, well, how would you do a differential over a ribbon cable? Well, that's also painfully simple. You have ground, and we'll call it signal 1 plus signal 1 minus ground. And then we might have signal 2 plus signal 2 minus ground. And I've then run out of, I haven't got enough on there. So if I was doing a differential down of, say, RS, say 422, for example, this might be. Or if I wanted to put I2C over a cable, because I2C, SPI are actually board level communication buses, but you could run them over a cable. And what I do and have done in the past, when I've wanted to run those over cables, I've always gone and converted the I2C or the SPI to a differential, and then I'll use this sort of topology in order to shove it down a cable. And trust me, that will work. So the other thing which I read whilst putting this show together for us this evening, I've never seen this, but I found it in my book, so I thought I'll share it. The other way which they mentioned in the book, is to actually put a ground plane under the cable. And obviously that would be that'd be tied maybe to that one there. So having a ground plane actually underneath, that would work. You could, of course, if you had EMC problems, it depends on the length of the cable, of course. You could, of course, have a wraparound if you wanted. Again, these are what I would call EMC tricks. So there is, I'm trying, hopefully you can see that from just colouring it in a little bit.
I've definitely seen ribbon cables wrapped in foil.
Yeah.
Or not even necessarily completely enclosed, but with a foil external to the cable itself.
Yeah, yeah. So what they're trying to do is to cut the radio emissions, which will be sort of irradiating off this thing, something terrible. Okay, right. Let me move on and talk about another part of the cables, which one of my pet subjects on is, here's some real top tips. It is EMC. If you want to fail EMC, which is a legal requirement of any product you may be making, if you're going to sell it, of course, a hobbyist, who cares? But EMC, if you want to fail, always put a cable on every time. If you're like next month, we're going to talk about medical devices. The EMC standards for radio immunity for a medical device is really, really tough. And if you've got cables going on, and say any device, medical, weighing scales, I guarantee you're going to have problems every time. A few years ago, I got to design these scales for M&S, new scales, which work brilliantly. But at EMC, we had problems with radio emissions on the immunity testing coming in over the cables and actually causing the I2C port to hang. We had to reset the processor in order to make the chip work again. So a problem caused by a silicon vendor, which was actually ST, so should have known better. So ST Microelectronics, who last quarter reported a $13 billion profit, because we had a cable and was injecting a lot of radio noise. The noise actually came in over the cables and actually caused the processor to hang. How did we fix that? So this is some real practical advice, which I'll share with you here. So if you've got a long power, this circuit here works brilliantly for power cables. So VX here and ground X. So this is your long cable. So this will be your long cable. All right, here, long cable. And this filter circuit will be on your board. So if you have the series of capacitors of 10 micro, 100 nano, 1 nano, you may or may not need 100 pico. It really depends on how much noise is coming in over the cable. Then a common mode choke, and this is a good one. And then the other side of it, you've got exactly the same capacitor configuration of, here we've got 100 pico, 1 nano, 100 nano, and 10 micro. And then this is obviously your circuit. If that makes any sense. So any noise coming in over the cable will then get filtered out before it ends up on your circuit board. And also works the other way. Any noise on your circuit board will get filtered before it ends up on the cable. And that will work every time. And that's in the downloads, so you can grab that. But what if you've got, say, a ribbon cable like we had here, and of course you've just got, say, a signal? How do you deal with it then? So this is how I deal with it, and this is actually what we have to do to solve an I2C problem. is the signal came in here, which will go SX for external. We had a capacitor here, 0 volts. Then we had a bead inductor. Then we had another capacitor. And then we'll have S, which was our circuit. We'll put circuit there, shall we? That makes sense. And this value here is probably in the order of about 1 nanofarad. So what I now do in all my designs, all the signals that come in over a port, every single one of them will go through this is called a pi filter. Every single one will go through one of these pi filters, and then I generally don't have the problem anymore. And this will also work if you've got an analog signal. So depending on what the frequency of the signal coming in is, because this will actually filter out any noise, or it may end up attenuating your signal if you've unfortunately got the numbers a bit off. But if you've got a slow varying DC, like a weighing scale, for example, or some other slow changing data, this will absolutely work and save the day. I think a little while ago, one of the people on this call, I think it was last year, had problems with, I think it says I2C port was hanging. And so I said, that is how you fix it. And I got that from a test house, and it's right. Okay, the last thing I've got here to share with you is, because this is cables and connectors, there's been a heck of a lot on cables, is on how to wire it up to a connector. So I did a bit of digging around, and going back to cable screens, there are good ways and bad ways of connecting up these screens. So they call this here, so you can read that, it says pigtail. I'll write it a bit bigger in case it's not clear on your screen. There we go, pigtail. Or another way of doing it is they have these eyelets, which basically shoved into the screen. And I haven't looked too much into any data, but the general gist of what I'm reading is that if you use an eyelet, you'll have much better screening than if you just twist the wires together. And I think often, I've got one here, so this is a RF connector, but probably not going to work really, is it? Does that even come off? This might be permanently attached, so that's probably a bad example. I don't want to break that. In here, then it's got one of these buried inside here. So this is actually, I think this is a Wi-Fi antenna. I did find, this is my last slide for us, is on connecting the ground in the connector. So this is a picture I grabbed. So here there clearly is no ground whatsoever. So this is bad. Don't do that. This is using the pigtail. So it's okay, but it's not brilliant. So that would be, this one here would be this one here. And I'm sure we've all done that, where we just twist it together. It's certainly better than doing nothing. But if you can, if you do a proper shield, like with the eyelet, and properly clamp it down, so this thick line around here is a proper shield, this will be by far be the best way of shielding a connector. And I grabbed a couple here, so this might look a little bit old school, but D connectors, this is a D sub here, and this is a one that's got solder buckets on the back. But I grabbed another one out the drawer. That's this is a PCB mounting one. So this is the shield round the edge. So, and of course, this shield round here has got these solder pins just here. This one here doesn't. So probably want to maybe try and mount that maybe in a metal housing. If you're having RF problems, you might get away with it without having to shield it at the end here. But generally speaking, talking with a few companies I know, most problems with cables that people have are start and stop with the connector failing. And I think in a lot of, so I think in wind turbines, for example, they'll actually monitor the temperature of the connector. Because if you've got a bad connector, then you're going to get an increase in resistance. And if you're putting a lot of current through it, then clearly you're going to start generating a lot of heat. I did have a bit of a dig around because of the world shortage of components. I had a little look as to what would be a good socket to go for at the moment if you're doing any work. And there's plenty of USBs for USB stuff. There's plenty, I've got a couple here, I see these two here. There's plenty of things like the RJ45. This is the screened RJ45. And this is an unscreened RJ45. So there's plenty of these kicking around. So differential, these would be differential signals going down these. They've found that there's plenty of D connectors. So non-differential, I'll probably go for maybe for a D connector at the moment. And there's a million of other connectors, but I'm finding they're available in such small volume. I think to steer away from them is my honest appraisal.
One thought, by the way, there are some RJ45 sockets which include a magnetic isolation transformer.
Yeah, there are.
So if you're not going to use it for Ethernet, be aware that you might not be getting a direct connection to your signal lines.
Yeah, you've probably got some sort, not quite, but yeah, you're probably some sort of magnetic arrangement. Well, you wouldn't have these inductors, capacitors on it. I think you've just got some sort of arrangement of those inside. Is that not right?
It's not. It's an actual isolation transformer.
Oh, it's isolation
the ones
transformer.
that have it.
Oh, okay.
There's an RJ45 is properly known as an 8P8C.
Does it look like that sort of thing?
Correct.
Yeah.
And so it entirely relies on magnetic connection.
Right.
It's for obviously for safety reasons, and actually also I believe it's got a relationship back to ground loops and things like that, because you don't want stray currents running between different equipment.
Yeah.
But anyway, it was just a warning that, don't use an RJ45 for something that's not Ethernet, where you're expecting all the signals to connect one-to-one to the wires.
Yeah. Because often you see the magnets often in these sockets, aren't they?
Yeah. So if you look at a really old, like PCI based, 32-bit PCI based thing, you'll often see that there's a large, like a supersized IC, which is actually the magnetic inductor part of the socket, and that'll be beside the actual socket.
Yeah.
And that in modern times has been integrated into the socket itself. So just be aware if you're using it for other reasons. Obviously, if you're using it for Ethernet reasons, it's a good thing.
Well, absolutely, because RJ45 generally is for Ethernet.
But the reason I mention this is that another very common use of RJ45 is for serial terminal consoles, RS232. I don't know quite, but I don't think that you would use the isolating transformers for that sort of application.
No, I mean, in fact, design which I'm working on at the moment for stuff with wind turbines, because the cables are so available, I'm actually using an RJ45, which is 4 twisted pairs, to actually send the data between, my boxes of trick. Although it's not Ethernet, it's 4 twisted pairs, and it's a great way of safely taking the data off one board and onto another. Obviously, it's one of these connectors. I mean, you can see it's just so small. There's definitely no magnetics in that, and I think you can probably tell by the price as well whether it's got anything inside it. Anyway, that is what I wanted to share tonight. So that's 5 topics on types of cables, horses for courses, voltage drops in cables. So if the cable's long and you're sending a lot of current down it, you can expect to have an appreciable voltage drop. So be wary of that. Shielding, different ways you can do shielding, and ribbon cables or twisted pairs, shielded or screens. EMC is my favorite subject, because usually, it's mentioned with cables, cables will emit noise, and of course they can also be susceptible. In fact, a little anecdote. A project I worked on, must be about 15 years ago. It was a device for measuring the profile of car tires. So it shone a laser at a car tire and gave it the profile. Now they had a problem with some radio emissions at, I think it was about 27 megahertz, and the harmonics thereof every 27 megahertz, because radio emission problems start recording at 30 meg. But the issue which they had was, by pure bad luck, the width of a car was pretty much exactly the quarter wavelength of the radio noise being generated by the equipment. And of course, because they had to have 1 sensor under each car tire, the length between them was a quarter wavelength. So they got the maximum amount of noise coming off the cables. We fixed it with a lot of filtering, of course. So that's always the best way of fixing these problems. You do, in fact, I've got some here actually. Talk about cabling before I let you all go. I'm doing some work at the moment with these are called split ferrites. So these can go around any cable to try and cut any noise problems, emissions that you might have. And the place you put these, in fact, there's one even here. Look at that. What are the chances? The place you normally put these ferrites, if you're trying to solve a emissions problem, is at the source. So on this one here, so this is actually coming off the camera. This choke is actually at the wrong end of the cable. This should actually be at the other side of this lens with the wires coming out of it. That's where the choke should actually be. So it's actually at the wrong end of the cable. And so another project I've been working on recently, another medical device. Depending on what end we put the choke, affected the noise coming off the cable. So we could work out at what end was all the noise being generated. So because we had a long cable, say 2 devices, say one here, this one here, and this one here. Because we put the choke at this end and we still had the noise, it means that was the problem. As soon as we put the choke at the other end, we don't get the problem, which proves that this is the one that's generating all the noise. That's another talk for EMC and ferrites on cables, which are very good at suppressing around about 50 megahertz. Anything outside of that, they're not so great. Anyway, does anybody want me to go over anything again or any more thoughts?